Hi everyone. In this video we're going to look at angles inscribed in circles. If you have an angle where the center of the circle is right at the vertex of the angle, that's referred to as a central angle. If that central angle measures theta, then so does the arc it intercepts. If you have an angle where the vertex is on the circle itself, then that's referred to as an inscribed angle. And if theta is the measure of this inscribed angle, then this arc it intercepts turns out to have a measure of 2 theta. And it's that relationship that we will prove in this video. To prove it, we'll break it into 3 cases. In case 1, we'll consider the case where the center of the circle is on one of the sides of the inscribed angle. Call the inscribed angle theta, and we want to show that this arc it intercepts is 2 theta. To do that, I'll draw this radius, making an isosceles triangle since radii are congruent, and therefore these base angles are congruent, and so the missing angle in this triangle is 180 degrees minus 2 theta. But since we have a straight angle here along the diameter, that means this angle out here is 2 theta. But that's a central angle, and the arc it intercepts has the same measure. So we've proven that arc has measured 2 theta in this case. For case 2, we'll consider the case where the center of the circle is inside of the inscribed angle. We'll call the measure of the inscribed angle theta, and again we want to establish that the arc it intercepts is 2 theta. To do that, I'll draw the diameter here that goes through the vertex of the angle, and I'll call this angle down here alpha. That angle marked alpha actually falls under case 1, so we already know that the arc it intercepts here is twice alpha. Now consider this angle up here. That angle comes from taking theta minus alpha. And that angle also falls under case 1, so we know the arc it intercepts is twice that, which is 2 theta minus 2 alpha. Well, if I take this arc on top and this arc on bottom and add them up, then I get the desired result, that the total arc intercepted by the inscribed angle is 2 theta. And finally, in case 3, we'll consider what happens if the center of the circle is outside of the inscribed angle, like this. Well, let's call the measure of the inscribed angle theta, and let's draw a diameter going through the vertex again. Let's say this angle here is alpha. Well, that angle again falls under case 1, so the arc it intercepts is 2 alpha. Well, consider the entire angle right along there. That comes from the angle theta plus the angle alpha. So that means this entire arc is twice that, 2 theta plus 2 alpha. Well, if I subtract those two arcs, the larger one minus the smaller one, I get the desired result, that this arc intercepted by the inscribed angle is 2 theta. So that proves the inscribed angle's measure is half of the arc it intercepts. However, there's a little more to the story. I want to extend the result. Let's consider the case where the inscribed angle is made up of, instead of 2 chords of the circle, a chord and a tangent line. And in that case, we'll consider 3 separate cases. Suppose your inscribed angle has one side as a diameter of the circle and another side a tangent line to the circle. So this angle here is our inscribed angle we will call theta. the arc it intercepts is defined to be the arc from the point of tangency along the right side of the circle to this opposite point on the diameter. And we'll call that arc right there beta. Well, I want to show that beta has twice the measure of theta. Well, we know another theorem that says that a radius drawn to a point of tangency makes a right angle with the tangent line. So that means theta is 90 degrees. Also, beta is exactly half of the circle here, so beta is 180 degrees. So again, we see the same relationship. The inscribed angle has a measure half of the arc it intercepts. Now in case 5, let's consider an inscribed angle like this one, where again, one of the sides of the inscribed angle is tangent to the circle, but this time the center of the circle will be inside of the inscribed angle. Okay, so we're going to call the inscribed angle here theta. And the arc it intercepts is defined to be this arc from the point of tangency along the right side of the circle to this far point on the chord here. And I want to establish that that measures 2 theta. To do that, I'll draw a diameter again through the point of tangency, like that, and I'll notice that I've got another right angle here. Well, let's call this angle alpha. That's a regular inscribed angle made from 2 chords. So from our earlier cases, we know that the arc it intercepts is 2 alpha. Well, the measure of theta in this case is 90 degrees plus alpha, and the arc it intercepts comes from 180 degrees plus 2 alpha. And that's exactly twice the inscribed angle. So one more case to consider. What if we have an inscribed angle made up of a chord like this and a tangent line like this? Let's call that angle theta. So the arc it intercepts runs from this point of tangency along the right side here to this point on the chord. And I want to show that that's 2 theta. Well, again, I'll draw this diameter, making a right angle with the tangent line, and we'll call this angle alpha right there. So angle alpha intercepts this arc of measure 2 alpha. Well, if I call the arc intercepted by theta beta, then beta is exactly equal to 180 degrees minus 2 alpha, since the right half of the circle measures 180 degrees. But theta comes from the 90-degree angle that's marked here minus the alpha. So again, that's exactly half of the arc it intercepts. So in all cases, if one of the sides of the inscribed angle is a tangent line, it again measures half of the arc it intercepts. Thank you for watching the video.